So now we're going to look at finding counterexamples to our conjectures, which is, like we talked about before, what we're really trying to do when we make a conjecture, because that's the only way to really prove that it's true. So if you can't disprove it, then it must be true. Oh, sorry about that. There's a knock at the door. Okay, so we're actually trying to disprove our conjectures. And sorry, my writing is going to be off today because my pen is off-centered and I can't center it. Disprove our conjecture. So by disproving conjectures, we find counterexamples, and then when we find those counterexamples, we make our conjectures better. And the stronger you make your conjecture, the more likely you are to make a proof, which we'll talk about next unit or next section. So counterexamples are examples that don't work with or follow our conjectures. Okay, and we'll see some examples of this, but basically it's just an example. You say, the least amount of rain, like we did last class, least amount of rain is in August, but then one year you have, a lot of rain in August, more so than in most other months. Then that month, that odd month, disproves your conjecture. So this is also the method that we use to test and improve our scientific theories. So in science, we aren't trying to prove our theory, we're trying to disprove it. Because if you cannot disprove it, then that proves it. Okay, and this is why this is the difference between a theory and a law. So like the law of gravity, the law of relativity, the law of conservation of energy, these things have not been disproven and we don't think they can be. So they are a law. But a theory is something that we're working to disprove. So this is why things like evolution is called a theory of evolution, because while we have a lot of evidence, we don't have every piece of evidence we need. And so it's still a theory. So the first example, these are some more simple ones. So we can show that each statement below is false by finding counterexamples. So if you live in Alberta, which is the province next to us to the left, you live in a province that shares borders with only other Canadian provinces. So is this true? So here you're in Alberta, it's kind of shaped like this, it's got a little bit of a cutout on the side where BC is. So we have BC on the side and Saskatchewan beside it on its left. So is that it? Is that the only border? It just has those two borders on the left and the right? So just take a minute and think about this, and you might want to pause the video here and try the next 4, and then just start the video up again, and then you can listen to my ideas. So this is false because it also borders Montana to the south. And if this were on a test and you didn't know which state it bordered, you could just say it also borders a state, right? So Montana would be down here. And then you could also say it borders the Northwest Territories, which are Canadian, but they aren't technically a province. They are a territory. So that also is false. Okay, our next one, a number that is not negative is positive. So, are there only negative and positive numbers in existence? Think about this one carefully. Again, try pausing the video and just think about it. These aren't trick questions. They're not supposed to be incredibly difficult. It's just getting you thinking logically. So a number that is not negative is positive. That seems true, but if I draw out my number line, I go -5, -4, -3, etc. And over here I have 1, 2, 3. When I get closer there, what happens between -1 and 1? What happens here? So there is 0, which is not negative or positive. So the conjecture that a number is not negative is positive is false, because 0 is not negative and it's not positive. all prime numbers are odd. Now, they love this question in math. This question sometimes shows up in university. They ask this question when they do like those street quizzes because people always forget about one prime number. So when people are thinking about prime numbers, I remember that prime numbers can only be divided by themselves and 1. So people always go, okay, like 1, 3, 5, 7, not 9, because 9 is divided by 3 also. And then you go 11, 13, again, not 15, 17, 19. And you can keep going and going and going. So everyone looks at this and thinks, yeah, they're all odd. They must be odd. Because any even number is divisible by 2, right? 4, 6, 8, 224. But most people forget about 2 itself, which is even, but it's a prime number, because you can only divide 2 by 2 or 1. And when we say divisible by, of course you can divide any number by a fraction, but this is divisible by a whole number. So this is wrong, because 2 is a prime number and 2 is an even number. And the square root of a number is always less than the number. Okay, so let's just try a couple. So like the square root of 4 is 2. 2 is less than 4. That checks out. The square root of, let's say, 16 is 4. 4 is less than 16. That checks out. Let's go, so if we keep going up, the square root of 25 equals 5. So if we keep going up, that seems to be true. But what if we go down? And again, let's use just perfect squares. So the square root of 1. What does the square root of 1 equal? It equals 1. And 1 equals 1. So that is not true, because 1 is not less than 1. Then let's try, how about the square root of, so we'll take our perfect squares here, we'll put them into fraction form, 0.25. So the square root of 0.25, and you can put this into your calculator, is 0.5. And 0.5 is greater than 0.25. So that is also untrue. And you can keep playing around with the numbers, and that's important when you're doing conjectures. Just play around with the numbers. That's what you're supposed to be doing. Sometimes you'll be able to see it right away, and sometimes you won't. So just try putting some numbers in, seeing where you get. So this doesn't work for numbers between 0 and 1. And of course, we can't take the square root of a negative number, so we just have to look from 0 up. Okay, so example 2. Let's look at this pattern. So the product of 11 and another 2-digit number. And remember that product means that we're multiplying by. So you'll see we have all these 11s down here, and then we've chosen other numbers in this column. So I want you to pause the video and look carefully at these numbers, okay? Now, remember like when we did the adding the fractions. So see what the sums are, see how we rearranged the numbers, try some division. Again, it's just observations and conjectures. It's very difficult to have a wrong conjecture as long as you can prove it, okay? So don't get caught up that you need to think of one answer, okay? You just need to think of a logical answer that has evidence. So pause the video, check this out for a minute or two, and then come back and we'll see what conjectures I make. Okay, so when I look at this, and I'm just looking at I looked at the sums to see what's happening there. And I noticed a pattern that the digits here, so the multipliers, are the first and the last digit here. So if I call the first, so if I say that this is AB times 11. That's the general formula here, right? AB being whatever number is first, and they're all multiplied by 11. So when I found that what I got was A and B were on either side, right? 43 is 473. 26 is 286. 12 is 132. So I had A and B on either side of the number, but then I have this middle number, the 2387. And that has a different pattern. So when I look at that, and again, so just try multiplying, dividing, adding things. When I look at those middle numbers, 2, 3, 8, 7, in relation to the AB, I notice that it's the sum. So 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 6 is 8. And 4 plus 3 is 7. So I notice that that is A plus B. Okay, so A plus B is in the middle of A and B. So what conjecture can we make about this pattern? Basically, I'm just going to put this into a sentence in here. So I said that the product, and if you don't want to say product, you can say when you multiply by the product of 11 and a 2-digit number, so just a number with 2 digits, right, 12, 26, 43, whatever, will follow the pattern of AB times 11 equals A, whoops, no bracket there, A plus B, B. So how can we test this conjecture? We are going to gather more evidence. So let's just pick some numbers, and we'll want to go both bigger than the 11, or smaller than the 11 and 12, and then bigger on the other side. So let's try 10 times 11, 14 times 11, 19 times 11, how about 27 times 11, and 28 times 11. So let's first write what we think it would be. So I think that this would be, so 1 and 0 would be on the end, and then in the middle would be 1, right? Because 1 plus 0 is 1. So this would be 110. I think that, according to my conjecture, this would be 1 with a 4, and then it had a 5 in the middle, because 1 plus 4 is 5. Now, the next one, 19, I think that this would be 1 and 9, and then 1 plus 9 is 10, so I don't know what I have to do. This is a question mark, right? Because I can't put 10 in there. Well, let's put 10 in there and see what we get. 27 times 11, so I'd say that this is 2 with a 7 and a 9 in the middle. And then 28 plus 11. So we'll do 2 and 8, and again we have another 10 in the middle. So if we do these on the calculator, so take 10 times 11, 14 times 11, 19 times 11, etc. 10 times 11 is 110, so that one supports it. 14 times 11 is 154. 19 times 11 is not 1,109. 19 times 11 is 209. So that does not fit. 297 is what you get when you multiply 27 times 11. And then when we multiply 28 times 11, you get 308. So that also does not fit. So did we find a counterexample? Yes, we did. And using this counterexample, we can revise our conjecture to say that the sum of AB must be less than 10, right? Because if it was more than 10, like 2 plus 8 was 10, not 1 plus 9 was 10, that doesn't work, right? Because you put the 10 in the middle, and that's 2 digits, and it's too big. And if we want to, or if I asked you to, you could continue to find more examples. Okay, so let's look at this last example here. So consider the difference between consecutive perfect square numbers. So a perfect square is 4 times 4, 3 times 3. Consecutive would be in a row. So 4 squared minus 3 squared would be 16 minus 9 equals 7. 7 squared is 49, minus 36 is 13. So 2 students, Thomas and Ray, looked at these 2 patterns and made these conjectures. So Thomas said the difference between perfect squares, consecutive perfect squares, is always an odd number. And Ray conjectured that the difference is always a prime number. So is it possible to have 2 different conjectures about the same problem? Of course it is, right? Everyone could have a different conjecture. So in this case, neither, so 0, 1, or both could be true. So both Thomas and Ray could be true. One of them could be true, or neither could be true. And we have to find counterexamples. So let's just try a couple consecutive perfect squares. So 2 squared minus 1 squared equals 4 minus 1 equals 3. And so this is odd, and it's prime. So far it is for both of them. Let's go a little bit bigger. Let's try 13 squared minus 12 squared. And you get 169 minus 144. And that gives you 25. So that's odd, but it is not prime, right? 25 can be divided by 5. And we can try, let's try 10 squared minus 9 squared. So you have 10 squared minus 9 squared equals 100 minus 81. That gives you 19. That's odd and prime. But because this one here, and you can just keep going until you find one that doesn't fit, this means that Ray's conjecture is wrong. But what do we know about Thomas's conjecture? So far, it's still valid. Thomas's conjecture is still valid. But we haven't proved it to be true yet. Because we haven't yet found a counterexample. And we've only tested 5 consecutive prime numbers differences in total. So we would need to do a lot more to prove Thomas's true or not. So in summary, all you need is one counterexample to prove your conjecture is false. So it's usually a lot easier to prove your conjecture is false than to prove it is true, because if you want to prove it's true, you have to look for every single case. So when we talk about inductive reasoning, because next week we'll start deductive reasoning, inductive reasoning can be used to make a conjecture, which is just an observation based on evidence. If a counterexample is found, the conjecture is found to be false. Or sometimes you'll see invalid. It's the same word. If a conjecture is found to be false, it can be revised so we can make it better. And we did that in this one here. So we said here that it would be A, B with A plus B in the middle. And then we revised it down here to say the sum of AB must be less than 10. We could continue to test it. If we find another counterexample, we could make our conjecture even more precise. Okay. And then lastly, inductive reasoning can never be shown to, never be used to show a conjecture is true. So that's when we use deductive reasoning. Because inductive reasoning in practice or in definition is to go from one example or a few examples into a big sweeping conclusion. And we know how many numbers there are, and so that becomes very, very difficult. So you can work on these problems in the textbook. Make sure you're also working on worksheet 1.1 and 1.3, which is on the back of 1.1. It's only half a page. On Tuesday, we will have a small partner quiz on what we've learned so far. So again, the key here is just to practice thinking logically. Go back in the video and try the questions again. And then when you're working through the worksheet, again, don't try to find what you think, I think is the right answer. Just find things that are logical and that you can back up with evidence. Email me if you have any problems, and I hope to see a lot of you here to do some corrections, and have a nice weekend, and I'll see you on Tuesday.